It's a great pleasure to have with us Matt Zaremsky from Albany, and he will tell us about the state of the art around the Boone-Higman conjecture and the role of Thompson's groups.
Yeah, cool. Thank you. Yeah, well, thank you for the invitation. It's great to be here. I grew up in the Midwest, so it's great to be here and remember what the weather's like in August every single day. So, so I'm going to talk about kind of an overview of Boone-Higman stuff. That's, maybe I could have just called the talk that. Boone-Higman stuff. Basically everything I'm talking about is at least joint with, I'm not going to write his whole name out, Francesco Fournier-Facio. And I've gotten good at typing Xiaolei's name. I think I spelled that right, Xiaolei Wu. But I'll also touch on some joint work with like Jim Belk, Colin Blake, Francesco Matucci, James Hyde. And okay, so part one is what's the Boone-Higman conjecture? Boone-Higman conjecture. And we're going to sort of work through this. Part one is the vanilla Boone-Higman conjecture. Part two is going to be like a Thompson-like version, and then part three is going to be a relative version. And then there's a part four that I forget what it is. So what's the Boone-Higman conjecture? This is, we decided it was posed in 1973. Every finitely generated group with solvable word problem, embeds in, so every group that has this kind of not quite group theoretic property of having solvable word problems, it's like there exists an algorithm, there exists a Turing machine that blah, blah, blah. That's like, I don't love that. That's not like, that doesn't feel like a purely group theoretic thing. But the conjecture is that every such thing embeds in a finitely presented simple group. That's just group theory, right? Finitely presented simple group. So the conjecture is that this algorithmic property is really equivalent to this purely group theoretic thing. All right. Good, so that's the conjecture. It's been open for 53 years. Is that? Yeah. Wait, oh, yeah, question.
Finitely presented simple groups have solvable word problems? Oh, sorry.
Remark, yes. So the converse is true/easy. And like predates the 70s. And so basically, I'll just say this out loud. So first of all, if you embed into a group with solvable word problem, you have solvable word problem. So the converse is really saying that, right, finitely presented simple groups have solvable word problem. Why is that? Well, if you have a word that it's going to turn out it does represent the identity, you can discover that by just kind of taking your finitely many defining relations, looking at their conjugates, and multiplying them together, and you're eventually going to discover your word. So finite presentability tells you that the yes part of the word problem is solvable. And then why does simple tell you that the no part is also decidable? In general, the problem is that if you have a word and it's not representing the identity, that's a negative statement. How are you supposed to algorithmically check that something doesn't happen? Well, in a simple group, being non-trivial is equivalent to normally generating the entire group, and that's a positive property. So you just like take your word, toss it into the relations, you still have finitely many relations, and now just look at all possible, or finitely many defining relations, and now look at all the relations, enumerate them. You're eventually going to catch every generator, if your word really was non-trivial. So simple is a property that converts the negative statement of an element being non-trivial into a positive statement about it normally generating everything. So that's why the converse works. So this is, yeah, so the conjecture is that that's kind of like everything lives in one of those, that like that reason for having solvable word problem is like the main reason for having solvable word problem. And Boone and Higman, with a modification by Thompson, proved that at least every finitely generated group with solvable word problem embeds in a finitely generated, recursively presented simple group. So you want finitely presented. You can at least achieve recursively presented. So the conjecture is you want to turn the algorithmic property into a purely group theoretic property. There's still an algorithm happening here, so it's not quite what we want. But I don't know. So maybe then this is like yet more evidence that maybe the conjecture is true, that at least this weaker thing is true. All right. So yeah. What's that?
Was it Boone? Did he die in the 50s?
Maybe a different, but William Boone. He was born in Cincinnati. I know that. I think, yeah, maybe there's multiple Boones who did things. It's Graham Higman and William Boone. I'm from near Cincinnati, so that's the only reason I remember that. I looked him up, I'm like, oh, he's from Cincinnati, yeah. I don't know when he died, the 90s, I think. All right, so what is known?
Can I ask a question?
Oh, yeah.
So when you said about how to use the simplicity, you just used the fact that one thing doesn't, it's not true that normally generates.
Yeah.
It's
So
just the normal generation that you use.
pretty much, yeah. But your thing was arbitrary. You had your arbitrary non-trivial element. You need to be able to know that your arbitrary non-trivial element normally generates everything. So any non-trivial element's going to normally generate some normal subgroup. Simplicity tells you there aren't any other ones. It's everything.
So if I just have the normal rank condition, it's not sufficient?
There's weakenings. I mean, it is kind of overkill. If you have some special non-trivial element that's your favorite element, then if it's how would that work? If every non-trivial normal subgroup contains your favorite element, then you can algorithmically just check that one gets caught. So it doesn't need to be simple as long as I think it's called monolithic, if the intersection of all non-trivial normal subgroups is non-trivial. And there's other ways to kind of weaken simplicity. But yeah, so simple's like overkill. All right, so what's the easiest group with solvable word problem? The easiest interesting group with solvable word problem, probably free groups. So in a free group, the algorithm to tell whether a word represents a non-trivial element is you just freely reduce and then see if anything's left. End of algorithm. Do free groups embed into finitely presented simple groups? Well, yes. V, even T. So V and T were the first ever known infinite finitely presented simple groups, and they reveal the Boone-Higman conjecture for the free groups. So that's good. But as we saw yesterday, lots of stuff doesn't embed in T. And also V, even, this is slightly surprising if you didn't already know this, that in Thompson's group V, it's impossible to embed Z squared star Z. Even though V is enormous and there's so much room to move around, somehow free products don't play well. So this is due to Blake and Salazar-Diaz. So V is actually not that great of a Boone-Higman container. V doesn't reveal the Boone-Higman conjecture for all that many groups of interest. So we have to move on. But this is sort of an aside. I was listing things for where the conjecture is known. So that was easy example. if you already know that free groups satisfy some conjecture, then what might be the next class of groups that you wonder whether the conjecture also holds for them? If you already have free groups, well, hyperbolic groups, I suppose. But this is way harder. Hyperbolic groups, but they satisfy the Boone-Higman conjecture. BH. And this is Belk, Blake, Matucci, 1T, 2Cs, I believe. And we did it in 2023, but I think it got like published like a month ago, if I remember emails correctly. Hyperbolic groups. All right, so all the hyperbolic groups satisfy the conjecture. If you, for some interpretation, a random finitely presented group is hyperbolic, and so this kind of shows that the conjecture holds generically, right? If you pick a random thing, it satisfies the conjecture. So hyperbolic groups. What else? Here's another kind of hard. This was easier. I'd say this was easier than hyperbolic groups, but so geometric group theorists love hyperbolic groups, I guess. Also OUT-FN and mapping class groups, right? But so here I'm saying OUT-FN and mapping class groups of punctured surfaces. These satisfy the conjecture. Satisfy Boone, Higman. Every OUT-FN embeds into a finitely presented simple group. Not V, but some finitely presented simple group. And this is Belk, and Fournier-Facio, and Hyde, and me, and 25 maybe. Okay, so those are some things where it's known. Oh yeah, and I should have maybe first said GLNZ. This is actually, it wasn't phrased this way, but Elizabeth Scott in the 80s proved that GLNZ embeds in a finitely presented simple group. Hence anything that lives in GLNZ. And so you get like all rags nilpotent groups, you get all nilpotent groups. These all satisfy the conjecture.
Just GLNZ, or you can take any lattice?
Well, any lattice, I guess, just because they embed in some, right, any arithmetic group, everything is also fine up to virtually. So if you virtually embed in some GLNZ, then you're good. So I think arithmetic groups. S arithmetic groups might be open in general. I forget exactly, but yeah.
Do you know that they're generic in the space of marked groups?
A generic group in the space of marked groups. I mean, I don't know actually. That's a good question. If they're hyperbolic, then yes, but that's probably a different model of generic. So.
The generic groups will include all the isolated points as well. So.
This is also making me wonder if the property of satisfying the conjecture is like an open property or a closed property. Yeah, it's an interesting question. If the finitely presented simple groups themselves are isolated, that's not an if and only if. It would even be interesting if you could prove that all isolated groups satisfy the conjecture. That would already be pretty interesting, actually. Yeah. Okay, and rags, nilpotent. All right, what about things? So then what's so in geometric group theory, what's everybody's favorite groups where it's not known yet? I think probably the biggest one is OUT-FN and mapping class groups of closed surfaces. So we have kind of the base pointed versions, but we don't have the non-base pointed versions. And I'm frustrated that nobody seems to know whether out fn embeds into some ought fm. I wanted to just be able to cheat and be like, yeah, out f9 embeds into ought f20, but nobody knows. Probably not. So those, it's unknown. Cat zero groups in general. Open in general. Metabelian groups, strangely. Finitely presented metabelian groups. It's not known whether every finitely presented metabelian group embeds into a finitely presented simple group. Like, metabelian, come on, they're so little. And then also one-relator groups, kind of interestingly. One-relator groups. One-relator groups. The hyperbolic ones, yeah, but how does it work? The torsion-free ones, I guess in general, we don't know yet. It's a little unclear how to leverage the hypothesis of being a one-relator group. What do you do with that? So, all right, good. So those are some things we don't know. Oh, I can use the buttons to yeah. All right, so now I'm going to talk about Thompson-like groups. Oh, whoops. I need to use this board. Now I'll talk about Thompson-like groups and what I call the permutational Boone-Higman conjecture. So the thing is that so far, in every case asterisk, where we know a group satisfies Boone-Higman, the simple group in question, the finitely presented simple group we use to embed it into, is, without loss of generality, Thompson-like. Even if a priori it wasn't, so like the Berger-Moses groups, the Berger-Moses groups are finitely presented in simple, and they're just not Thompson-like at all. But nonetheless, they embed into finitely presented simple Thompson-like groups. The asterisk is till like 2 months ago or so. Kate reminded me there's a new one. Stefan Witzel and co-authors have a new finitely presented simple group that I don't know whether it embeds in a finitely presented simple Thompson-like group, but.
Where does this group come from?
It's Euclidean building of type C2 tilde, and you have like a lattice.
So these are analogs of the Capras-Remy?
Yeah, they're more closely related to the Capras stuff.
Are they torsion-free?
I don't think so. And those ones I also kind of view a little bit like Berger-Moses-like. So there's like Thompson-like things and then more Berger-Moses-like things. And this new one is over there. And I'll talk about mixed identity free at the end. The key thing is we don't know if it's mixed identity free. Anyway, okay, so let me tell you what these Thompson-like groups are. Twisted Bryn-Thompson groups. Twisted Bryn-Thompson groups. So Matt Bryn in 2004 came up with what's now called Bryn-Thompson groups, and then Jim and I, published in 22, like twisted them. So let me quickly define them. The input is a group acting on a set. Okay. Yes, all right, interesting. Faithfully at the moment at least. But okay, so given a group acting on a set, you can construct a thing. Here's what you do. You take, well, I'll write it this way and then maybe explain. You take the permutational Reith product of G acting on S with a copy of V for every element of S. So this is that, so you take a copy of V for every element of S. Think of them as lamps, I suppose. You have like a V's worth of settings on each lamp. And then G is just permuting the lamps around. G is just permuting these copies of V around. This naturally acts on C to the S. C is just the usual Cantor set here. And then to the S is the product topology. So you take a copy of the Cantor set for each element of S. I think of them as colors. So you have like different color copies of V. Now I have different color copies of the Cantor set producted together. And this action is the straightforward thing. The red copy of V acts on the red Cantor set. The blue copy of V acts on the blue Cantor set. And G permutes the colors. Yeah, G permutes the colors. All right, and then, so that's a perfectly fine thing. And then the twisted Bryn Thompson group SVG, so I don't know, we call it SV sub G, is the topological full group of that, is the piecewise-ification. Ification. Should piecewise-ification have that E there, I wonder? If the hyphen is there, then yes, I think the E needs to be there. These are the important questions. The piecewise-ification, so you look at, I mean, C to the S is itself a Cantor space. And you can like chop it into finitely many Clopin sets. And then an element of this group is just on each Clopin set, you do something that agrees with an element of the Reith product on that piece. But you can do like different elements of the Reith product on different pieces, as long as everything pieces together into homeomorphism. That's this. Does that make enough sense? So that's the group, and it's always simple. Always simple. And then probably need, no, I think I can fit this here. And then it's also finitely presented if and only if, so there's an explicit condition just on the action. You can detect finite presentability just from the action of G on S. It's finitely presented if and only if G itself is finitely presented, every stabilizer is finitely generated, and then the kind of weird one, the diagonal action of G on S cross S, so the action on pairs of elements of S, has finitely many orbits. So that's the weird one, because probably when I said a group acting on a set, in your head the set had some more structure. Well, maybe not. Maybe it was a bunch of dots. But if you wanted it to be a metric space or something, no. Because, if there was some notion of distance between the points, G is not going to respect it. You got to get down to finitely many orbits of pairs. Even if the pair of points is really far away, G has to be able to bring them close together. So think of it that way. I should mention this is actually exactly the set of conditions that ensure the Reith product is finitely presented. Cornulier proved that. So this is a situation where I had where I have this group and I take the topological full group, and finite presentability of the original group actually gives you finite presentability of the topological full group, of the piecewisification. This is, I don't want to say rare because I just don't know. This seems unusual in some way, but okay, good. So this is and it's easy. I don't know. It's doable to find examples of groups acting on sets with these properties. They exist. So I can produce finitely presented simple groups this way. Simple, finitely presented. Oh, and let me call this, an action of type A2 in square brackets, just because that's what it is in the paper. But there's such a thing as type AN, and we conjecture that if the action's of type AN, then the group is of type FN, like finiteness properties, but we don't know it beyond 2. Or I think we can do 1, 2, and infinity. We can't do 3. We can do infinity, but we can't do 3. So I'm just saying, don't worry too much about why is this called A sub 2 in square brackets. It's just, that's what it's called. All right, and now I can finally state the permutational Boone-Higman conjecture. Let's think. So now the permutational Boone-Higman conjecture is that every finitely generated group with solvable word problem embeds, let me call it gamma because it's going to start mattering in a little bit. Every finitely generated group gamma with solvable word problem embeds in a group G, admitting an action of type A2, hence embeds into a finitely presented twisted Bryn-Thompson group, SVG. Yeah, so this is stronger than the Boone-Higman conjecture. The Boone-Higman conjecture is you can always get into some finitely presented simple group, and now this is conjecturing the finitely presented simple group can always be one of those guys. Twisted Bryn-Thompson group. Yeah. G embeds in SVG. I guess I didn't say that out loud, but that's why the hence. If you get into G, then you get into SVG, just by permuting the coordinates of C to the S without breaking it up at all, without bothering to piecewisify at all. And like I said, basically in all but this one new situation, for this one new group that I forgot about when I was writing these notes, so far, anytime a group satisfies BH, it also satisfies PBH. So far. So the big question is, or I didn't say, BH implies PBH, does the converse hold? Wait, what? Oh, sorry. So PBH implies BH. If you embed into one of these finitely presented simple groups, then you embed into a finitely presented simple group. And the question is whether the converse holds. Are they the only game in town? Up to embedding. Okay. Oh, and I missed an important word here, sorry. Embeds in a group G, admitting a faithful, faithful action of type A2. Faithful was not part of the definition of action of type A2, but it was part of the definition of twisted Brent-Thompson groups. So, yes. Okay. This part of my notes, I was very scratchy. Did I miss anything important here?
Can I ask a dumb question?
Oh, yes, please.
So like the action of G on itself by left multiplication.
Preserves the word metric. And so if you have an infinite group, the action of G on itself by left multiplication preserves the word metric. And so you're not going to be able to have finitely many orbits of pairs. Yeah. So even if G is finitely presented, yeah, it satisfies 1, it satisfies 2, it's faithful, but fails 3.
For the Belk, it's going to be like the action on the boundary,
On the, in the hyperbolic case? In the hyperbolic case, the Horo function boundary turns out to be useful. And you have to kind of mess with the group a little bit first, but in the end, acting on the Horo function boundary is basically the thing, yeah. So boundaries are better than not boundaries. That's right. Yeah, okay, so I think that's the end of section 2. And now section 3 on relative Boone-Higman. Oh, and I was going to say, so yeah, so obviously the Boone-Higman conjecture is really interesting, and it would be great to figure out whether it's true. But over the years, somehow my brain has latched more onto this. This seems more tractable somehow. I don't know if it's true or not, but is it at least equivalent to the twisted Brent-Thompson groups thing? That feels, and if I had to, I would, this is being recorded, so I gotta be careful here. I would probably bet like $10 that the Boone-Higman conjecture is false, but that every time a group does satisfy it, it satisfies it thanks to a twisted Brent-Thompson group. I feel like if that ended up being the thing, I'd be like, yes, good. Like maybe they're, like if you could prove they're equivalent, and then you could argue that there's some crazy group with solvable word problem that can't act a certain way on a Cantor set. And so it can't embed into a twisted Brent-Thompson group that's finally presented, and so it can't satisfy the Boone-Higman conjecture. Somehow if these were equivalent, it feels like a good avenue to trying to prove that the conjecture is false. But this is complete hand-waving. Okay, good. So let me talk about the relative Boone-Higman conjecture. So let me define a few things first. A group, gamma, sharply embeds. There's so much chalk. I should use a good chalk. A group gamma sharply embeds in a group G if there's an embedding such that for all proper normal subgroups N of G, the image of gamma misses it. So if you embed, but you can't hide. You can't hide in some normal subgroup. You're in the group like legit or something. Sharply embeds. Equivalently, iota induces injections for all quotients, for all non-trivial quotients Q of G. So you embed it into G, and then it stays embedded even no matter how you quotient it, unless you trivial quotient. So that's sharply embeds, and I don't really, let me say, for example, simple groups. Wait, what? Oh, that's for the next thing. Sure, for example, if you embed in a simple group, then it's automatically sharp, is sharp, because there just aren't any proper non-trivial normal subgroups anyway. Right. Okay, and now, so that's kind of like a, so all this time we're talking about embedding in simple groups, and now I've weakened, I've strengthened the notion of embedding. Let me weaken the notion of simple. Wait, strengthen and weaken, I always mix up these things, but let me define that a group G is relatively simple. Is relatively simple if there exists a proper normal subgroup N called the largest such that all the other ones live in it. Proper normal subgroup called the largest such that every proper normal subgroup of G lives in that one. I've seen Google led me to something calling this one-headed groups. I don't know. I like relatively simple. It's simple if not for this little chunk. So relatively hyperbolic is like it's hyperbolic except for these chunks. Here it's simple except for this chunk. And of course, for example, simple implies relatively simple with largest normal subgroup, the trivial group. Largest proper normal subgroup, the trivial group. Relatively simple with trivial being largest. But there are other examples. Okay, so sharply embeds, relatively simple. Now I guess I'll put this here. Now I can state the relative.
Basically, you have a unique simple quotient.
That's, you do. That, annoyingly, that turns out to not quite be equivalent.
Does the Higman group satisfy this condition?
The Higman group?
Yeah, and the quotient is
Infinite. Can you have, I don't know. I think there's a lot of normal subgroups.
Asymmetrically, like it is a SQ universal.
Yes, yes.
Yeah. It's got a ton of normal subgroups.
You can have larger quotients. You want few small quotients.
You want, yeah, I guess that's okay if you have lots of big quotients. You just want one little quotient.
I mean, there's really no reason for it. But I don't know.
I'm trying to find the examples of
Right.
Yeah, the examples are about to appear eventually. I'll say out loud, just if you don't insist on the action of G on S being faithful, you can still construct twisted Bryn-Thompson groups. They're just not simple anymore, but they're still relatively simple. That's going to be the point here. Yeah, so relative Boone-Higman conjecture. Every finitely generated group with solvable word problem sharply embeds in a finitely presented relatively simple group. This is a relative version of Boone-Higman and analogously can pose rel PBH, where the I guess the analog is not so obvious. I mean, you sharply embed into a group G that admits a possibly non-faithful action on a set S of type whatever, and the kernel's the largest. So that's kind of, so the word analogously is doing a lot of work there, but let's just leave it like that. Okay, so what's a good, I'll bring that one. Oh, I spelled analogously wrong, but it's gone. So I'll state a theorem that'll also kind of serve to make it a little more clear what rel PBH is about. Whoa. Oh, and it's up there now, but just as a remark, the converse of relative Boone-Higman is true. If you sharply embed in a finitely presented relatively simple group, then you have solvable word problem. Kind of for the same reason. Being non-trivial, since you sharply embed, being non-trivial means you normally generate the entire thing over there. So basically the same argument. All right, so theorem. Now this is the main thing. Or two main things here. So first of all, given a possibly non-faithful action of a group on a set, we get an abstract twisted Bryn-Thompson group. We still just write SVG. It's just now that the action's not faithful, you have these regions of G that act trivially on the Cantor cube. So it's not a group of homeomorphisms of C to the S anymore. It acts on C to the S, just not faithfully. Maybe I should emphasize, not necessarily faithful. Not necessarily faithful.
It's still going to be an action by homeomorphism.
It's an action, it's just a non-faithful one, yeah. It's a non-faithful action by homeomorphisms on the Cantor set. And the image is, and the image is this. It's the twisted Bryn-Thompson group where now the group doing the acting, the group doing the twisting is this quotient of G, where you map out the kernel of the starting action. But yeah. But kind of the point is that, which is, first of all, relatively simple and finitely presented, again, if and only if this action is of type A2. And hopefully it's still up there. In the definition of type A2, G itself needs to be finitely presented, and there's no reason to expect that that's going to be finitely presented. So there's no reason to expect that this is finitely presented. So this can be finitely presented while this one's not. So the relatively simple group here is like better than the simple group here in the sense that it's easier for this one to be finitely presented. Because quotients of finitely presented groups don't have to be finitely presented. Okay, so that's this theorem that we can build these things, and then the actual here's the. All right, let me summarize, and then state our main theorem. So we have permutational Boone-Higman, which is like Boone-Higman thanks to Thompson groups. That implies Boone-Higman. If you embed in one of these special finitely presented groups, then you embed in a finitely presented group. And the big question is whether the converse is true. Of course, if you satisfy, if you embed into a literally simple whatever, then you're also satisfying the relative version. Right, like using a relatively simple group whose largest normal subgroup is the trivial one, largest proper normal subgroup. Same, we get a thing there. Okay, yeah, okay, and now the theorem is, I guess these are all last names. I could just write, I only need 2 Fs. The theorem is that, in fact, so I still don't know whether BH implies PBH, but it does imply rel PBH. So BH implies rel PBH. If you embed into a finitely presented simple group, even if it has nothing to do with Thompson groups at all, then you sharply embed into a finitely presented, relatively simple, abstract twisted Bryn-Thompson group. So up to moving the goalposts. Thompson groups do tell the whole story for some definition of the whole story. Let me say it in words. Every finitely presented simple group, and hence any subgroup of it, so anything satisfying Boone Higman, every finitely presented simple group sharply embeds in a finitely presented sharply embeds in a finitely presented abstract twisted Bryn-Thompson group. And since it's sharp, it also embeds in that quotient that I probably erased, which is literally simple, but there's just no reason to expect it to be finitely presented. So unfortunately, this doesn't, you can't straighten this arrow out to go that way, at least not yet, or yeah. But okay, so 12-ish minutes. That's perfect. So, okay, so we have the Boone-Higman conjecture, its permutational version, which really means kind of like a Thompson version, and now these relative versions. And the relative version allows you to reverse this arrow in a pleasant way. So now let me just talk about the construction of how you do this, just briefly, and then thoughts on trying to straighten the arrow out. I mean, it's not that hard to tell you what G is given gamma, so I might as well. So this is part 4, the construction and thoughts on BH versus PBH without the relative prefix. So what are we given? You're given your group gamma, your group with solvable word problem. We're assuming we already know it embeds, well now, okay, so here gamma was the simple group, but now gamma is your favorite group, and I'm going to call H the finitely presented simple group that a priori has nothing at all to do with Thompson groups, so think like a Berger-Moses group if you like. And now I'm going to embed that into this bigger group, which is kind of weird that this is not the first thing you would think of. Maybe it's the first thing James Hyde would think of, but so look, take your finitely presented simple group, think a Berger-Moses group, free product with a free group, n is at least 2, and look at all the automorphisms of that fix the H factor pointwise, that don't mess with H. So you can do whatever you want to Fn. You can also like bombard Fn with H. You just can't change H. I picture like matrix linear algebra things where you're attacking one thing with another thing. I haven't taught linear algebra for 3 years, but I have to teach it in the fall, so I have to remember how this works. Hitting one thing against another. This group, what does that act on? Well, it's a group of automorphisms from this, like maps from this to itself. So I probably want to have it act on the set of maps from this to something else. What's the something else? I'm going to just use H and have the subscript again mean like fix H. Homomorphisms of H star Fn to H, that when you restrict it to H, it's just the identity. So really, I mean, this is just H to the n. You just have to specify where the generators of the free group go, and they can go anywhere. Oh, and this is S Okay, so it turns out that since H is finitely presented and simple, this action is of type A2. I say that as though, yeah, turns out. That's a strong turns out. Yeah.
What is G here?
Oh, sorry. G. Or no. Oh, I didn't. G is this. Yeah. G is this, and S is this. And I barely remembered to call that S, and I didn't remember to call that G. Those are G and S. So gamma embeds in H embeds in G admits an action of type A2. So that's, there you go. That's rel PBH. And so all this stuff embeds into an abstract, sharply embeds into an abstract twisted Bryn-Thompson group that's finitely presented. If the action of G on S is faithful, then gamma satisfies PBH, not just the relative version, but the real one, because, well, yeah, because that's what PBH was, that you embed sharply, but I mean, the largest normal subgroup is trivial, so that's not really a thing anymore, into a finitely presented simple twisted Bryn-Thompson group. So if the action of G on S is faithful, then we're good. And it turns out for this particular G and particular S, this is equivalent to H being mixed identity free. Mixed identity free. And I'm not gonna, so there's no word, there's no element of H star Fn that dies under every such homomorphism to H. If there is something here that dies under every single map to H that fixes H, then it's called a mixed identity. And if you don't have any of those except for the trivial one, you are mixed identity free, or myth. Yeah, so where'd it go? So H was your finitely presented simple group that you managed to embed your favorite group into. Maybe it was a Berger-Moses group. If it's also mixed identity free, then you're in Thompson world. Even if you weren't, you are. Berger-Moses groups are mixed identity free. These Capras things, Kate proved these Capras things are also mixed identity free. So that's why that one we know PBH. And then this new one popped up, and I don't know. But and so what was I gonna? So right. So the annoying thing, or no, first, the nice thing about this is that since twisted Bryn-Thompson groups themselves are MIF, they're always MIF. For simple groups, if you admit a faithful, highly transitive action on anything, then you're MIF. And Thompson-like stuff tends to do that. So twisted Bryn-Thompson groups are MIF. Since they are, this shows that they are the universal finitely presented simple MIF groups. Every finitely presented simple MIF group embeds into one of these finitely presented simple MIF groups. But the annoying thing, not all finitely presented simple groups are MIF. For example, T. So, oh no, what about T? well, T embeds in V, and V is MIF. So like that's fine. You would just use V instead of T as your H in that case. But I don't know. I mean, so then there's the question, does every finitely presented simple group embed into one that is mixed identity free? That would be super great. I have no idea. I also don't have a good sense of how to like classify the mixed identities in T. That might also be useful. But so last thought, so like a general goal here, for H not mixed identity free, you can still look at G, where this is G still, this crazy thing that I don't want to write again, you can still look at G mod this kernel. So you mod out all the automorphisms that fix every homomorphism. So think if you like send every generator to itself times a mixed identity, then you're acting trivially over here. And well, I mean, so G was finitely presented and the action was of type A2. So you also had this thing about stabilizers are finitely generated, finitely many orbits of pairs. Those properties pass to the quotient, right? I mean, a quotient of a finitely generated group is finitely generated. That's fine. If the bigger group has finitely many orbits of pairs, ignoring the kernel's not going to change that. It's the same orbits everywhere. So the only question is whether maybe it is finitely presented. And ask, maybe it's still finitely presented. If you just kind of like mod out all the automorphisms that amount to hitting the generators of the free group with mixed identities, mod all them out. Is the resulting group still finitely presented? It's like, can all the mixed identities be realizable from only finitely many in some sense, in some somewhat complicated sense? I don't know. But that would then, like, if that were true, then you could straighten the arrow out, and then PBH would be equivalent to BH without having to write rel in front. Yeah. Okay, that's all I have. So thank you. Oh. Yeah.
Questions?
So this is really about the first part. So when there are constructions of embeddings, do they have anything to do with the algorithm that solves the word problem?
No. So right, basically anytime that somebody has managed to embed a group with solvable word problem into a finitely presented simple group, the fact that the word problem was solvable is irrelevant. The algorithm doesn't feature in the proof, and you just don't. Anytime this has happened so far with an embedding, you're using properties of the group, I guess, but of like what it is. If it's a hyperbolic group, you're using hyperbolicity. If it's a hyperbolic is equivalent to a word problem solvable in linear time. So like maybe somewhere in there is lurking, like you could maybe phrase it as since the word problem is solvable in linear time, blah, but I don't know. Yeah, solvability of the word problem is a very strange hypothesis to try to use.
When you have a type A2 action, you can use that action to extract a solution to the word problem. So an algorithm.
Yes.
Like there's an algorithm that's kind of hidden in the action itself. So that's kind of the connection, right?
Yeah. So for right. So in the original thing, for the simple group stuff solvable word problem, there was this argument. And then for the permutational thing, also, yeah, if you admit an action of type A2, you can solve the word problem kind of by hand, it turns out.
But this A2 condition is your invention, right?
Yeah.
And it did not exist in 1970.
No.
So why
The original motive, so it's exactly what makes the wreath product to be finitely presented, and so we were kind of like, oh, maybe it's also the thing that makes the twisted Brun-Thompson group be finitely presented. And
I think you didn't state the Boone-Higman theorem.
yeah, I did. It's erased now. Yeah, where'd it go?
Because that was the original motivation.
I'm sorry, I missed that.
The Boone-Higman theorem states that any group with a recursively presented group with a solvable word problem embeds in a simple subgroup of a finitely presented group.
I didn't phrase it that way,
They
but
constructed that. And
So
they-
out of an algorithm, they do construct
Yeah.
embedding.
yeah.
Yeah. And they ask, can the simple group be just assumed to be the whole group? Like, can you just get a finitely presented simple
Yeah.
group instead of a simple subgroup of a finitely presented group?
Using the Higman embedding theorem, that's the same as embedding in a recursively presented simple group. So at some point I said recursively presented simple group, and then I dismissed it. But yeah.
What's the dependence of the little n here?
Not very. It really just works for any n greater than or equal to 2 here. And so might as well use 2. I think, yeah. N is 2.
So at the very beginning, you said that you mentioned that finally presented plus simple implies that the word problem is solvable.
Mm-hmm.
You said something about weakening that is an overkill.
Yeah, so in a simple group, there's a smallest non-trivial normal subgroup, namely the whole one. And if you have a group with the property that there's a smallest non-trivial normal subgroup, then, wait, am I saying that right? If there's some element that the normal closure of every non-trivial element contains that element, then that's good enough to give you solvable word problem, and you're finitely presented. So in simple, this guy can just be anybody, but it's enough for there to just be one best non-trivial element that gets caught by every normal closure.
Then why don't you ask? Then why don't you ask like to embed into the group like this? Like you're trying to prove a converse, and the theory group is not using the full strength of the.
Yeah. So, well, wait, but so you're saying like maybe first try to embed into that type of group. If simple is too difficult, first try to embed in, yeah.
Go from something very strong to
Yeah.
word problem, but you're not using the full strength, so there's something in the.
Yeah, it's definitely true that
It goes midway.
simple is heavy overkill for, I don't know. I feel like Boone and Higman knew that, and they still conjectured this. So it would be, so those are called monolithic groups, I think. It would be cool to prove that every finitely presented monolithic group embeds in a finitely presented simple group. And then you could be like, see, there's no chance of it being easier. Yeah.
I think just for historical reasons, it is.
Yeah. If you found a counterexample, then we can, yeah.
Yes, what were the result of it? Besides the result of Scott, before you got interested in this conjecture?
GLNZ, I mean, like certain self-similar groups, like work of Rover. Rover essentially proved that the Grigorchuk group satisfies the Boone-Higman conjecture. And in general, more like Nekrashevich groups for other self-similar groups. Yeah. But
Yeah, but there is a gap like of 20 years.
yeah, nobody kind of touched this for a while, I think. And now there's been sort of a flurry of activity. So, yeah.
Thank you so much.